Hello everybody, welcome to lecture 13, the introduction to the t-statistic and the one-sample t-test. Before we jump into this lecture, I feel it's probably appropriate for us to do a little bit of housekeeping so I can give you guys some perspective as to one, where we've been so far in the course, and two, where we're probably going to end up going for the rest of the semester, okay? So this lecture, it officially marks the beginning of the second half of the course. And, you guys have really grown a lot. You're not my little baby statistics machines anymore. And frankly, that's kind of hard for me. One second. I promised myself I wasn't going to cry. Okay. It seems like just yesterday you guys were little statistics babies, right? You were doing things like pooping your pants when you saw the syllabus and how much work the course was going to be, or crying when you had to learn statistical notation and the rules of summation. But we powered through that and we got through it all together, and you guys have been growing consistently since the beginning of the course. And after that you learned about z-scores, and you learned how to do what seemed like 50,000 versions of the z-score formula and different z-score problems, right? And you learned about hypothesis testing and that four-step process that we use when we're doing inferential statistics. And man, I was such a proud papa at that point. And to extend our analogy a little bit further, if you started the course as little newborn baby statistics machines, at this point, given all the considerable growth you have made, I would probably say you are little toddler statistics machines at this point, okay? You're fully potty trained, you're asking to drink my beer, we're playing the pull my finger game, and we're having a pretty good time. It's great. And, it's funny in a lot of ways because we spend the whole first half of this course essentially teaching you the language of statistics, teaching you how we do things, letting you learn how hypothesis testing works, make sure you understand statistical notation, because that stuff really does form the basis for everything that we're going to do. But the thing is, you guys learn those z-scores, and z-scores and those z-score problems, they're great, right? You guys probably feel like you were awesome because you could do an inferential statistics problem. And, the thing with z-scores, they're great, but we hardly ever use them for a couple of reasons. The first reason is that, the z-score problem requires you to have information about the population that you typically don't have access to, for one. But we also use them because, they're useful for helping teach you guys the language of statistics and of hypothesis testing. And so that's why we sort of start with there. Now, again, if you're just little statistics machines, little toddler statistics machines at this point, to extend our analogy even further, by the end of this course, you will be fully grown college statistics machines. And so we clearly have a long way to go. You learned about one type of statistical problem. Going forward, the next section of the course is about the t-test, which is 3 different types of tests. So the next 3 lectures, you're going to learn about 3 separate types of analyses. After that, we do one-way and two-way ANOVA, and all the things that come with those things. And then after that, we do correlation and regression, and then we do chi-square. So there's still 6 of the 7 or 8 things that we have to learn throughout this course ahead of us in the second half. And so you guys should buckle up because things are going to start moving really, really quickly. But we've spent the whole first half of the semester giving you the basics of the course so that you can understand the language. And trust me, things are going to move extremely quickly going forward. And so I think we should go ahead and start this lecture so you guys can sort of get a feel for what I mean by that, okay? So without further ado, let's meet the t-statistic and the one-sample t-test. The learning outcomes for this particular lecture are for you to understand and know when to use the t-statistic instead of a z-score hypothesis test. 2, for you to perform a hypothesis test using the t-distribution. And 3, for you to understand the concept of effect size and to also be able to calculate it. And there's 2 of them that we're going to learn, maybe 3, I suppose, because R is one of them itself. But we're going to learn Cohen's d, and we're going to learn about the percentage of variance accounted for, and then we'll also learn about confidence intervals, which are super fun. So let's do it. So there are 3 types of t-tests that you're going to learn over the next 3 lectures, and each one has its own formula for the t-statistic and the corresponding DFs, which stands for degrees of freedom, which I'll teach you about shortly. Which of those formulas you use for any given problem depends on the characteristics of the sample and the design of the study that you did. And so I'd like you to go ahead and pause the video for just a second so that we can go ahead and together become familiar with the new formula sheet that we're going to be using going forward. So somewhere in one of the folders for the formula sheets in Blackboard, you should be able to find a formula sheet that looks something like this. So let me X out of here real quick. And not that thing, but this thing, okay? And we're going to zoom in on this puppy. This is your new best friend for at least the next 3 lectures. This is the t-test formula sheet, and each black line separates them. So there's 1, 2, 3 separate formulas for t, depending on what type of t-test you're doing. And I know right now that thing probably looks overwhelming, but trust me, there's ones way crazier than this. And frankly, you've learned the statistical language and our statistical notation stuff, so you know what all this stuff means. And even if you don't, you'll be able to read it and follow it. So again, things like this, right? That's the sum of squares. Well, we learned definitional and computational formulas for that way back when you were still little statistical babies. So that's sum of squares. So it's sum of squares divided by degrees of freedom. And ultimately, you sort of care about this version of things for the one sample t-test. It just shows how you get to the easy version of the formula. For the independent groups t-test that we'll learn next time, this is the formula. And so it's still got this mean difference on the top between 2 groups. And then we get some estimate of the standard error, but it looks more complicated than it is, but that's just the sum of squares for one group and the sum of squares for another group, which you use this formula to get for each group separately. And then you have to divide that by n for each group a bunch of times. So this looks kind of scary and daunting, but it's really not. And then finally, we have the related samples t-test. And so it sort of boils down to this formula. And you haven't learned what D is, but essentially it's just a difference score. So it's the difference in subtraction between a set of scores. So you have one set of scores and another set of scores, and you get the difference, and you just plug that stuff into here, and you should be able to follow the form of that, right? So again, it's going to be some type of mean difference over some estimate of a standard error to get t for all 3 versions of the t-test. It's just different ways that you sort of get there. Okay, we can still also calculate confidence intervals, and I'm going to introduce you to this idea of this thing that we call effect size today. And so we'll learn a couple of different ways to calculate effect size, and you'll know what that means shortly. So this is your new best friend for a little while. You're going to have to become pretty familiar with this, and you're going to get one of these for pretty much every section of the course going forward. So this will be your best friend for like 3 days, and then, you'll get a new best friend essentially, is how this will work. And these things get clearly complicated, right? Like if we didn't even have a formula sheet for the Z test, right? You guys just have to memorize the one formula. Well, now look at this. We got 3 separate formulas, and it's kind of nuts. It takes a whole page just to give you all this information. So that is your formula sheet. It's your new best friend. So let's go back here and back into full screen mode. So the first one that we're going to learn about today is called the one sample t-test. And the one sample t-test, it's used when you know the population mean, but not the standard error. So we don't know what the population standard deviation is. And if we don't know that, then we can't divide it by the square root of n for our sample in order to get an estimation of the standard error to use the z-score formula to do our hypothesis testing. So z-test is out now, right? Because we don't know the population standard deviation and can't figure out the standard error. When you're doing the one sample t-test, what you're going to do is you're going to collect data on one set of people. So you have one sample that you're collecting data on. And what you ultimately want to do is compare the obtained sample mean, right? So the mean of the people who are in your sample, you want to get their average, and you want to compare that with the average in the population. And it sounds a lot like the z-test. And in fact, it pretty much is exactly the same with one small twist, right? You don't know the population standard deviation, which Dr. Hale used to always give you. And then you would just divide that by the square root of n in your sample when you had a z-score of a group, right? And then that essentially gave you the standard error, and that let you solve for your z. So that's sort of the big difference. So again, I basically took a screenshot of this from your formula sheet, right? And so basically the one sample t-test, t equals the mean of the sample minus the population mean divided by an estimation of the standard error. And basically the standard error in this particular case, it used to be the population standard deviation. So rho divided by the square root of n is what that used to be. But now it's not that anymore. It's going to be this, right? And so this is going to be the sample variance divided by n, and you get the square root of all of that. But frankly, if you just sort of rearrange that, you can just know that the sample variance, the square root of the sample variance of s squared is just s, right? So if you get the sample standard deviation, which you know formulas to do, you can then divide that by the square root of n. So this ends up being the formula that we know and use all the time. The second type of t-test, that is the independent groups t-test. And the independent groups t-test, that's used when you don't know the population mean or the standard deviation or the standard error, right? So we don't know anything about the population. And what we do with the independent groups t-test, the design for this is when we collect data on two separate samples. And what we want to do with this particular group is we want to compare the two obtained sample means with each other. And so again, in this test, the sample means are independent of one another. That's the magic word there. And this means that you have one set of individuals in like an experimental group, and you have another set of individuals who are completely different and non-overlapping and not related in a control group. So you have these two groups that are not related to one another, and you get the means, and you want to compare those two means to one another when you're doing an independent groups t-test, or you might see it called an independent samples t-test, but it's the same thing. And the independent groups t-test, this is used when you have a between subjects design, right? And that's what we mean by you have these two separate, distinct set of groups. So to take this back to an analogy that we've used in an example earlier, right? You guys remember the Mortal Kombat versus Animal Crossing study that we did earlier in the semester, where we had some kids playing Mortal Kombat and we had some kids playing Animal Crossing, and we wanted to determine whether the kids who played Mortal Kombat engaged in more violent acts after playing the game. That would be an example of a between subjects design, right? Because there was no kids who were playing Mortal Kombat who were also playing Animal Crossing, and it wasn't like we had brothers over here and sisters over here or other brothers over here, right? And the two separate groups, they were distinct and independent groups, right? And so that's a between subject design. Here's a screenshot again of this particular formula for this. I just grabbed that from your formula sheet. And so you guys can see that it sort of boils down to this, and I'm not going to go too far into it because you'll get an entire lecture on it next time. I just sort of wanted you to be able to see that this formula looks different, but at the end of the day, it's still exactly the same thing. It is a mean difference between two means, except we don't have a population mean now. We just have a separate mean, which is going to now be the mean of a control group. So it's still going to be a mean difference, and all of this stuff for all as complicated as it looks, it really is just an estimate of the standard error of both samples put together. The final one that we're going to learn is the related samples t-test, which some people call the dependent groups t-test, or yeah, I think those are two major names that you'll see out there for it. This is used when you don't know the population mean or the population standard error, okay? And there's two basic ways or two different designs that we use when we're conducting a related samples t-test. The first method is for us to go out and get two groups of people which are matched on some variable. So we go out and we get subject A and we give him like an intelligence test, right? And then we go out and we find another person who has pretty much that exact same intelligence test score, right? So they all both have the same IQ. And we're going to put one of those people in the control group, and we're going to put the other person in the experimental group. And the idea is that these people are similar in some meaningful way. And so we match people across conditions. The second way that we do this is we do the related samples t-test when we have repeated measures taken on subjects. So again, we can give people an IQ test, right? And then we can say, all right, we're going to figure out what your IQ score is, and we give it to all the people in the group, right, that we're going to look at. And then we can say, we're going to have everybody in this group take this pill that's supposed to increase intelligence. And then we can measure them a week after they take the pill to see if they're smarter. Okay. And if we did that, we kind of have a pre-test and then we have a post-test, and we can actually see if the change over time or if the difference between those groups is statistically significant. So we have a mean for the pre-test scores and we have a mean for the post-test scores. And we want to find out if those things are different. And if our pill worked, right, you would expect these people to be smarter a week later than they were before. So their IQ scores should go up, and we can test that. And the way that we do that is with a related samples t-test. The related samples t-test, again, it basically boils down to this. On the top, it's the sum of all of these differences divided by the number of differences. So again, it's basically a mean difference, just like all the other t-tests and just like the z-test. And then all this stuff down here, for as complicated as it looks, it really is just an estimate of the standard error. So these things all take the exact same form, right? It's a mean difference over the standard error, and you just have to do a bunch of crazy things depending on what type of formula it is to get those things. And it's not really the top part you ever have to worry about. It's always the bottom part that gets extremely complicated. So let's talk about the t-statistic, which is an alternative to the z-statistic, right? So we know that a sample mean, if you have a large enough sample, it essentially estimates and approximates the population mean, right? If you have a large enough sample, let's say about 30 or so people, then, you know, any 30 or so people, you get this normal distribution, and you probably get a fairly decent estimate of the population mean for most things using just a sample of 30. Now, the standard error, right, if you guys remember literally what it means, it describes how much difference is reasonable to expect between the population mean and the sample mean on average. And so we can basically go back and forth between these things, right? We know that the standard error of the mean is basically equal to the population mean divided by the square root of n, or you could just get the square root of the variance, right? So that's rho squared divided by n, right? So the only difference between these two things is that you already took the square root of that, and so you just still need to get the square root of the bottom part of n. And so these are basically the same formula, right? In terms of the z-score statistic, right? So what we've done so far with the z-score distribution and those different types of problems that we did, we used the z-score statistic to quantify inferences about the population. And what we always had, right, we had an obtained difference between our data, right, what we found in the sample that we did, and some hypothesis, which was some population parameter or some population mean that I gave you as part of the formula. Okay, and then we had to get the standard distance between M and U, and the way that we did that is that Dr. Hell typically would give you the population standard deviation, right? And then all you had to do was divide the population standard deviation by the square root of n if it was one of those problems in which you were doing a z-score with a group, right? But that formula always works even if it's a group of one, and so either way it goes, that's how you got z. Now, what we did is we used the unit normal table, right? That was that 4-page monstrosity that you had to sort of go through and hunt for the right sort of magic number for what you were doing, even though I just gave you which numbers we typically use. But then you still had to use that to find what percent of scores were above the z or below it. And so you got very, very familiar with that. And guess what? You will never have to look at it ever again, right? You can basically take that thing and throw it away. But we use the unit normal table to find those critical regions of z-scores to find a normal distribution. That's what the whole point of it was. And we knew that when n equals 30, like that's when we could use it, or we could use that unit normal table when the original distribution was also approximately normally distributed. Now, there's a couple of problems with z-scores, right? I think I said at the very beginning of this lecture that I've never used a z-score in real life out here in the work that I do. So for those of you who don't know, I do research on PTSD. And so we're often trying to study whether, you know, one treatment for PTSD works better than another, or whether there's some sort of special thing that we can do to make our treatments more effective. And we typically do this sometimes with t-tests, but a lot more fancier statistical things as well. But we never use z-tests, and we really never use z-tests because computing a z-score requires much more information than you typically have, right? When you're doing studies, you don't always know the population mean, even if you can sort of guess it or sort of determine it rationally, right? But even if you can get the population mean, you almost never have the population standard deviation, right? That's like, you never have that. And frankly, if you had that, right, if you had all that information, sure, you could always sort of want to know whether a particular sample sort of differs from the population mean for your study. But if you understand the entire population, you don't really need to do inferential statistics, right? That was sort of the whole point of that, right? We're trying to understand the nature of how a sample is related to the population. But if we already know this important information about the population, what's the point in going out and getting a sample? There's no real point of it. We have all that information already. So that's the problem with z-test. This is why we don't typically use it. What we typically have is just sample data. And so we get around not knowing the population standard deviation by estimating it from our sample. So again, with all of these t-tests, right, you sometimes have the population mean and sometimes you don't, but you never have the population standard deviation. And the way we sort of deal with that is we just estimate it using our sample, right? So t-statistic, the t-stat is an alternative to z, and you can basically call it an approximate z. And the estimated standard error, right? So it's now, instead of being rho with an M, it's now going to be SM. So remember that from our definitional and computational formulas from way back when, that was the difference between them when you were talking about a sample versus a population for the standard deviation and the variance. It was rho versus S, and now it's just going to be SM. And that's used in place of the real standard error when the value of the population standard error or standard deviation isn't known. So, how do we get this estimated standard error? Well, we're essentially going to use the sample variance, right, which is S squared, and you guys remember the formulas for that. We're going to do that to estimate the population variance, which is rho squared. It's fairly straightforward and simple. So again, the estimated standard error simply is just going to be the standard deviation of the sample, right, divided by the square root of n, or if I give you the variance, you can just basically divide, you can do the division first and then get the square root of all of it, and these two things are functionally equivalent. There's no difference between them from a mathematical perspective. And the estimated standard error is used as an estimate of the real standard error when the value of the standard error is unknown. So we have to figure this out, and we just sort of use that as a stand-in for what the real standard error is in our population. Now, again, the t-statistic, they all follow the same form, okay? It's always going to be some difference between two sets of means, okay? So we have a mean for a control group and a mean for an experimental group, or actually I said that backwards. It'd be a mean for an experimental group and a mean for a control group, and the independent groups t-test. For the one that we're going to learn today, right, it's going to be the difference between some group that we go out and get versus some population mean that I'm going to give you. So it's not, you don't even have to figure out the second one. And then for the related samples one, right, it's always going to be sort of the pre-test minus the post-test, or, you know, group 1 of people and versus group 2 of people, but they're matched in some sort of way, right? So it's always going to be a mean difference on the top, the difference between two means, and the bottom is always going to be some estimate of the standard error, and it just varies in terms of how we calculate that depending on which formula we're using, okay? So we're always going to have the estimated standard error in the denominator for the t-statistic. And that's literally the only computational difference for this formula, for the one that we're learning today, right? So the only difference between the z-statistic and the one sample t-statistic is that instead of having the bottom part be based on the population standard deviation, it's going to be based on the sample standard deviation. That is literally the only computational difference. So it makes a nice little segue here, right? Again, all three types of t-tests boil down to this exact same sort of form, but there's differences in how we get the different parts. But really, the differences come from the denominator part. It's this bottom part that we have to do different things to get in different ways. And then you also have to look up the critical values in a different way now. But the new table that we're going to use, so you have another new best friend we're going to meet here shortly, that table's much more easier to navigate than that 4-page monstrosity that we had to always wrestle with when we were using z-scores. And so in some ways that part of it gets easier, but the math gets a little more complicated. So you get all those crazy formulas now that you have to do. But the formulas, for as crazy as they look, really aren't that crazy, I promise. And you've already learned all the language you need to know in order to be able to solve them. So the t-statistic, it's used to test hypotheses about an unknown population mean, which is mu, when the value of the population standard deviation is unknown. Okay, so we're basically trying to compare a sample mean to a population mean when we're doing the t-statistic, though, for the one sample t-test. And we're going to take a bit of a segue here, right? Not much of a segue, but a small one to explain to you this concept that we call degrees of freedom, okay? When we are trying to do these t-tests, right, we have to get some estimate of the sample mean, right? Or of the sample variance, actually, right? Because we have to turn the sample variance into the sample standard deviation, and then we have to divide that by the square root of n. Well, when we're trying to compute the sample variance, we first have to get the sample mean, okay? Because remember, to the sort of definitional formula of that, we had to take each score, subtract it from the mean, and square it, and we had to do that for every single one of the scores, and then add them up. That was the definitional formula of the sample variance. And we divided that by n minus 1, I believe is how we did that before, to get the sums of squares, right? And the thing is, when you're doing that, right, if you're saying I have to have in order to get the sample variance, I have to know the mean. Well, that essentially means that only n minus 1 score, so n is the total number of scores you have, and only n minus 1 of those scores in a sample are independent. So if we have 10 scores, and we say these 10 scores have an average of 15, okay? 9 of those scores get to be whatever they want, right? But if you remember the lessons we learned about the mean, it's this balance point, right? If you know what 9 of those scores are, right, that 10th score can't be whatever it wants to be, right? It has to be whatever value it needs to be in order to make that mean be what the mean is, right? And so researchers call that n minus 1 thing, they call it degrees of freedom. And we denote that in our formulas going forward, and this is a very important concept to understand. We just call it DF, right? That stands for degrees of freedom. And for the one sample t-test, because it varies depending on what test you're using, how you calculate the degrees of freedom. But for the one sample t-test, it's going to be n, which is the number of scores you have, minus 1. And so you need to sort of just understand that we have to calculate this thing in order to look up our critical values in our table. And it varies depending on how we do it. And I'll show you on the formula sheet where you find the degrees of freedom formula for each type of statistical test that we're going to do going forward throughout the rest of this course. Now, the degrees of freedom are particularly important in the t-distribution for 2 reasons, okay? The first reason is that we talk about the t-distribution like it's just this one sort of curve, like the z-distribution, right? It was based on the unit normal curve, right? That symmetrical bell-shaped thing that we've come to know and love. But the thing with the t-distribution actually is it's not a single curve at all, like the z-distribution. What it really is, it's literally a distribution of curves, right? It's a family of curves. It's 1,000 of them or something like that. And each one of them differs in shape based on the degrees of freedom for the test, okay? And so it looks pretty much like the normal distribution. And once you get to about an n of 30, they're pretty much the same. So I guess it's maybe 30 different curves. Maybe I overestimated that. Because anything over 30, the z-distribution and the t-distribution are basically indistinguishable. But when you have less than 30, the t-distribution looks different from the z-distribution. Not a lot different, but it's 2 things. It's flatter than the z-distribution, and it's fatter in the tails, okay? And I'm going to show you a picture so you can actually see what I mean by that. Now, again, you have to figure out what the degrees of freedom are when you're doing this as part of your hypothesis testing, because you use the degrees of freedom for the test in conjunction with the alpha level, right? So before it was always just alpha, and whether it was a 1-tailed or 2-tailed test that we were doing that let us figure out what the critical value was for z, that number that we had to beat. Well, now it's not just alpha, and it's not just the number of tails that you're using, whether it's a 1-sided or 2-sided test. You also have to account for the degrees of freedom for the test, because again, the distribution changes depending on what the degrees of freedom are. And what I mean when I say it changes, I mean that the proportion in the tails vary depending on what the degrees of freedom are. So you have to look that up in the table too. But interestingly, in a lot of ways, while that may sound like that's going to make the tables nuts, like it was 4 pages before, it's going to be like 100 pages now. No, it's actually just 1 page. It gets much simplified when you have to do this, because we don't make you look up every single plausible value. We sort of pick ones that we think are sort of interesting and typically are things you're going to see. And those are the only ones we put in the table. So, the distributions of the t-statistic, again, like I said, the t-statistic is not, the t-distribution is not a single curve, okay? It's a family of curves, okay? And so again, it's fatter and flatter than the z-distribution. So this is what the t-distribution with the degrees of freedom of 5 looks like. So if your degrees of freedom are 5, right? If we're talking about a 1-sample t-test, then that means you had 6 people, because it's going to be n minus 1. And so this is what it looks like. And notice when it's flatter, right? The fewer people you have, this is the shortest one, so it's flatter than the other 2, which are the t-distribution when you have 21 people with 20 degrees of freedom, and the normal distribution when you have 30. Okay, and so you can see basically the normal distribution is here. If we had a t-distribution with degrees of freedom of 30, the z-distribution and the t-distribution are basically the same. But less than 30, you see it's different. And it's different because it's flatter, for one, but it's also fatter in the tails, okay? So what we mean by that is, right, for 5, right, notice it's shorter overall, but out here it's bigger. And out here being bigger means that there are more scores out here, right, for when it's 5 than when it's 20, right? And so you can see how these things vary. And so you can't use the z-distribution, at least until you get out here at 30 degrees of freedom. And that's why when I'm going to show you the table, I'll show you that, we have a lot of values that are less than 30. And then basically after 30, we don't really care anymore. Okay. So let's see what that looks like. Again, the t-distribution, it's a family of distributions, right? Each one with its own value for the degrees of freedom. And at a certain point, n equals 30, that number keeps coming up, right? That number came up somewhere earlier, right? When we're talking about the central limit theorem. But it basically approximates the shape of the normal distribution. So it still has that bell-shaped symmetrical curve, but it did have this thing where it was going to be flatter than the normal distribution, and it's more spread out than the normal distribution. And then it's actually got more variability in the tails than the normal distribution. And so we have to use a table of values for t in place of the normal unit for our hypothesis test. So we can't use that z table anymore. And a lot of you are probably saying, thank you, God, because that table was awful. And I hate it, and I never want to look at it again. And so right now what you can do is you can take that table, those 4 pages, and you can ball them up and throw them away because you'll never have to look at it again. You can set them on fire. You can do whatever you want. Just don't burn your house down. Make sure if you're going to do that, you have some water or extinguisher or something, because I personally will not be held responsible if you happen to burn your house down. Don't be stupid and do that, okay? So I want you to go ahead and pause the video here now, and we're going to take a second to become acquainted with our new table, okay? And so go ahead and find this thing. It should have been somewhere in your formula sheets or in your statistical tables folder in Blackboard. And just pause the video, print it out, and then come back to the video, and I'm going to explain to you what we use this thing for and how we use it. And so again, I didn't stop. I just sort of pretended that you guys actually paused the video. So if you didn't, that's going to feel really weird, but we're just going to let it ride. This is a screenshot of it, right? So this is sort of what the first 8 rows of that table look like. To find the critical value for any statistical test that you're going to do, you have to know a couple of things, or determine a couple of things. First, you have to determine whether you're doing a one-tailed test or a two-tailed test, okay? And so if you're doing a one-tailed test, you have to look up what the alpha level is next. So what column you look in to figure out what the value of t is that you have to beat, which are all these numbers here, right? To find that magic number, you have to know whether it's one-tailed or two-tailed, and then you have to know what the alpha is, okay? And so if you're doing a one-tailed test of alpha of 0.05, here's the one you would look in, right? You'd look down this column, and then you would look at the corresponding degrees of freedom, which for the one sample test is going to be n-1, okay? So you need the degrees of freedom as well. If you were going to do a two-tail test at alpha 0.05, you're not going to look in this column anymore, right? Because this is for one tail with 0.05, and this is two tails with 0.10. So if I said that, that's where you would look in this row for. You're going to do two tails with 0.05, you go to the next one over, right? Because it's two tails with 0.05, and then you're going to find the corresponding degrees of freedom anywhere from 1 to 60 or whatever that table goes down to, okay? So let's sort of walk through a couple of them together. So you guys have your tables, and if you don't have it out, just look at it here and see if you can figure it out with me. What is the critical value for a one-tailed test with alpha 0.05 at 8 degrees of freedom? Okay, so you would have to find one tail, that's what I need, and then you would say I'm going to find 0.05. Okay, so we're going to go there, and then we're going to go down to 8 degrees of freedom, which meant we had 9 people in this study or whatever, right? So we're going to find one tail, 0.05, and 8 degrees of freedom is going to be that number right there, and it's going to in fact be 1.860. That's how you use this table, okay? Fairly straightforward, right? How about a two-tailed test with alpha of 0.05 and 3 degrees of freedom? You can either pause the video and then figure it out, or I'll just go really slow when I look for it, but I want you guys to take a swing at it first, and maybe I'll just sort of ramble on here incoherently to give you time to do that, and hopefully you've gotten there by now, right? So we're going to do a two-tailed test, right? So instead of using this first row of numbers here, we're going to use this second row because we're looking at a two-tailed test, and we want 0.05, right? And so two tails, 0.05. And we're going to do 3 degrees of freedom. So it should be the third number down for 3 degrees of freedom. So what you should have said is, Dr. Hale, it is 3.182. Cool. That's how you use the new t-table. It's a lot easier to use, right? This is way easier than trying to go and find, whether it's column B, C, or D in the z-table and then make sure you had all that stuff right. We don't have to do any of that kind of crap anymore. We're super excited. So this is basically a recapitulation of the stuff that we just figured out, right? So the t-distribution for a one-tailed test with alpha 0.05, degrees of freedom of 8, that's negative 1.86. It could also be positive 1.86, right, depending on which way you're predicting. So here we predicted something that would be less, and so you're going to put all that 0.5 over here. This is 5% of your scores. But if we said it would increase intelligence, like for our pill example, right, we're going to put all of it over here, so it would be positive 1.86, but because it's one-tailed, it's just going to all be on one side. And so it just happens that we made the picture so that it would show a negative prediction. This is the same one for a two-tailed test, alpha 0.05 with 3 degrees of freedom. So 3.82, positive and negative, right? Because it's two-tailed tests. And because it's two-tailed, just like with the z-distribution, you're going to take that 5% alpha, that 5% chance that you're willing to make a type 1 error or be wrong in your prediction. And we're going to split it in half. We're going to put 2.5% over here, and we're going to put 2.5% over here, right? So again, just the same thing in a different way. Now, when n is small, when n is less than 30, what do we know about the t-distribution? Let's do a learning check here. Is it identical in shape to the z-distribution? Is it flatter and more spread out than the z-distribution? Is it taller and more narrow than the z-distribution? Or, whatever, we can't tell. Well, I said it several times, right? The answer for this should be B. It is flatter and more spread out than the normal distribution, right? That's the thing about the t-distribution relative to the z-distribution. But once you get to 30, they're basically the same. Okay, so this brings us back to the first test we're going to do, right? So you guys understand the z-distribution. You know how to use your table to look up the critical value that you have to beat in order to declare it significant. But now we have to figure out how do we get that number that we're going to compare to the number we have to beat, right? So we're going to calculate a t-statistic, right? And the way that we do that, we get a mean difference between a group that we care about or that we have data for and a population mean. And we're going to divide that by the sample standard deviation, which we're probably going to have to solve for. So hopefully you guys put that formula in your brain like I warned you to several weeks ago or days ago, depending on which version of this course you're taking. And you're going to divide that by the square root of n, okay? And so this ends up being what you're going to do, okay? And it makes things fairly straightforward. So after we solve for the t formula, we're basically going to do our hypothesis testing. And remember, I told you guys, I said, we're going to do hypothesis testing and we're going to always do those 4 steps. So all that stuff about stating the null and alternative hypothesis will haunt you for the rest of this course and the rest of your life if you keep doing statistics. We're going to always state that the null and alternative hypothesis, and then we're going to select an alpha level. After we do that, we're going to locate the critical region on our distribution using the alpha and the number of tails that we're using and the degrees of freedom, right? Because we just showed how that mattered for what we're trying to figure out. After we do that, we're going to calculate the t-statistic, and I just showed you how we do that with the formula. And after you do that, you basically compare the t that you came up with to the t that was the critical region, right? This separated the reject the null versus not rejecting the null areas in your distribution from step 2. And once you do that, you just compare them and then you draw your conclusions, okay? So this is just like the Z stuff, right? So this is not terribly different in any meaningful way from what you already know how to do. So let's do an example, okay? And I'm going to show you sort of what I would typically give you in terms of a question on an exam and how you solve it. So again, there's this long-standing phenomenon studied in social psychology, and it's called the better than average effect. And don't read on, like, just if you don't read on because I don't want to spoil the story, we're going to do a little experiment because this is what I do in the in-person version of the class. So before I even tell you what the better than average effect is, I want you guys to do me a favor. On a scale of 1 to 10, go ahead and write down how attractive you think you are. And we're going to say 5 is like just a perfectly average person. So on a scale of 1 to 10, with 5 being average, how attractive are you? And even Dr. Hill is going to play along with this. This is one of my most fun things to do. So go ahead, think about what you are, look in the mirror or whatever, find a picture, look at a selfie, whatever, and write what you think you are. Just so you guys know, I wrote strong 7.58. I didn't say you couldn't use decimals. That's your fault if you didn't think to do that. So I'll explain why that's going to be funny in a second, okay? So the better than average effect, what it is, it's this phenomenon that we study in social psychology for 50 years now. And basically what it boils down to is this idea that if you tell people to guess they're standing on some trait like I just did, right? I said, how attractive are you? And you also tell them what the range of the scores are and what the mean is, what the average is. What people tend to do is sort of to rate themselves as better than what the average is, because nobody wants to be worse than average, right? And so I can almost guarantee you, right? I told you guys on a scale of 1 to 10, with 5 being sort of right in the middle. What did you say you were? And I said I was a strong 7.58. And I can almost guarantee you in the class of 60, there would probably only be about 4 of you who said something less than 5. And even the people who said something less than 5, they might have been like 4.96, right? Nobody's going to say that they're less than attractive or really further down less than attractive, right? Nobody's going to be like, I'm a 2, right? But guess what? That's how averages work, right? Most people are going to be of average attractiveness. That's literally how averages work, right? And so everybody can't be 9s and 10s, right? Although I'm certain if you wrote 9 or 10, you probably are as attractive as you think you are. Maybe. We'll see. So, now, again, Dr. Hale and Dr. Pillow, we didn't believe that this thing was true, right? That can't be right. Like, people are realistic. People sort of know what they really are, right? People aren't going to do this kind of thing. And so, what we typically do, every semester, I do this with, attractiveness for, one example, but we also do it with driving, okay? So, what we could do? We could basically say, I'm going to poll 10 random people, and I've done this, and these are the numbers that I sort of came up with, right? I got 10 students, and I said, hey, on a scale of 1 to 100, tell me how good a driver you are, okay? And what they told me, here were their scores. Somebody wrote 35, someone said 70, someone said 82, so forth and so on. And again, we said on a scale of 1 to 100, and on a scale of 1 to 100, right, 50 should be average, right? Even if I don't tell you, like, people should sort of intuitively understand that, if 100 is like best driver ever and 1 is worst driver ever, then 50 is right in the middle. And so you would expect an average driver to say, yeah, I'm about a 50. And you can sort of just look at these scores, right? And these are real data that someone gave us in class one year. There's only 2 scores that are below 50, right? And look at that guy. That guy's like, I'm modest, right? That's like, maybe I run a stop sign every now and then. And this person, they were probably the most accurate, I suppose. This guy, man, he thinks he's like the best driver ever. So does this person. That's weird. Nobody's ever really that good. But this is what we did. So we went out and collected the data. This is our sample, okay? So we got a sample of how many people? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I started counting, and then I looked up there and I saw that it said 10, but I had started counting, so I had already committed. I kind of had to stick with it at that point. Otherwise, it would have looked really dumb to stop counting at 3 and then just say 10 out the blue. But yeah, so we got 10 people, and that's our sample for our study. And if we have 10 people in our study for one sample t-test, or I've said this several times now, the degrees of freedom for this test, right, are going to be n-1. So our degrees of freedom are going to be 9, okay? Now, we're going to test whether or not the better than average effect is real using this data that these students gave us. And we're going to test it with alpha 0.05, and we're going to test it in one tail. And we're going to test this in one tail, right, because it's called the better than average effect. There's no reason to suspect that those scores are going to be worse than average. So we're going to take all that alpha, right, that whole 5%, and we're going to put it down on one end of the distribution, right, on that better end, on the right side of the distribution is where we want to put it, right? So we're going to do 0.05 alpha and one tail. So we got to state our hypotheses. That's always step 1, right? We got a null hypothesis and we have an alternative hypothesis. And for the one sample t-test, it's different for the rest of them that we're going to learn going forward. But for the one sample t-test, your hypotheses look just like the z-test, right? So again, the first one is going to state what happens if nothing happens, right? If the better than average effect isn't real for driving, what would you expect to happen, right? We would expect that the mean of the students is equal to 0. So again, HO colon mean of the students is equal to, sorry, not 0, but 50, right? Because that's sort of where the middle is. And this is exactly how you would write this if this was a z-test, okay? What would the alternative hypothesis look like? Well, first of all, we said that this was a directional test, right? So I want you guys to go ahead and maybe pause the video if you want to try to guess it. If you don't want to try to guess it, then I guess, you'll just sort of see me show you in a second. But it's going to say H1 colon, the mean of the students is greater than 50, right? Because it's the better than average effect. So the alligator mouth is going to eat the mean of the students, okay? So that's our hypotheses. Absolutely nothing new for step 1 of our 4-step process from going from a z-test to a t-test. Literally nothing different because the hypotheses are written the exact same way. Okay? That brings us to step 2 of our 4-step process. We have to set the criteria for making a decision, right? We have to figure out what's the critical value that we have to beat in order to say that we're going to reject the null hypothesis. So the first part of that requires us to draw a sampling distribution and label the areas where we're going to reject versus retain the null hypothesis. And then after we draw that sampling distribution, we're going to define the values of the critical region based on the alpha level, the degrees of freedom, and whether it's a 1-tailed or 2-tailed test, right? And so for the one sample t-test, which I've now said like 1,000 times, I feel like this is that one lecture where I said distribution of the sample means 1 billion times. But again, you're going to use degrees of freedom, which are going to be n-1. And remember, we had 10 people, so it's going to be 9, which means whatever our answer is going to be somewhere on this row, right? But we have to figure out also which column it's going to be in. So remember, we said we're doing a 1-tailed test with alpha 0.05, and degrees of freedom are going to be 9 degrees of freedom. So our magic number theoretically should be somewhere in there. So first thing we're going to do is we have to draw our sampling distribution. But whether this number is going to be positive or negative depends on what side we draw it on. Now remember, we said this is the better than average effect, right? And so if it's better than average, if average is in the middle where most of the scores are going to be, then better than average is going to be on this side. So we're going to define the labels where we're going to reject versus retain the null hypothesis as follows. We were basically going to put it down here, and we said if we get some number that's out past whatever this thing's going to be, we will reject the null hypothesis and say that the better than average effect is real. And if we get a number that's smaller than whatever we get for here, we're going to retain the null hypothesis and say that it's likely that the better than average effect is not real, okay? And so again, we have to now figure out what's that magic number that we have to beat going to be. And so again, we said we're doing a 1-tailed test with an alpha of 0.05 with 9 degrees of freedom. That should be 1.83. Yes, it in fact is 1.83 is the number that we're trying to beat, okay? So that's the end of step 2. We've done step 2 when we've done all of this, right? We've drawn our sampling distribution, we've labeled our areas where we're going to reject versus retain the null hypothesis, and we've defined what that critical value actually is. So step 2 is done. Step 3, we have to calculate our test statistic, okay? And so in this particular case, what do we know about the test statistic? It's going to be the mean of our sample minus the population mean divided by the standard deviation of the sample over the square root of n. Okay, so we can figure that out pretty easily. So that's our magic formula, and the degrees of freedom for our test are going to be n-1, which I've said again. Take a shot. Every time I say degrees of freedom is n-1, maybe I'll make that a game now, okay? So that's our formula that we're ultimately going to use, okay? Now, again, there's a lot of stuff involved in this, right? Because before, when you had a z-test problem, right, the most work you had to do is you had to get the mean, maybe, and you had to get the standard error because you had to divide that by n. Now you have to do a little bit more work, okay? Because you're now toddler statistics machines, and you can handle some of this responsibility on your own, right? You can go and tie your own shoes, or you can pick your own outfit out now, right? Because that's what toddlers do, and you guys are toddlers now. So you're going to have to solve for the mean, which you always had to do before. I'm still going to give you the population the population mean. I'm going to give that to you most likely. You'll be able to count to figure out what n is. You'll just count the number of scores, and you're going to have to solve for the sample standard deviation. I'm probably never going to give you that. And remember, I used to always give you the population standard deviation when you were a baby. But now, no, you have to figure this out on your own, okay? And so the way that you do that, basically, of course, the mean is basically going to be the sum of all the scores, which is what that means, divided by n. And you're going to use the computational formula for the sample standard deviation, which is the square root of the sum of all the x scores squared. Square all the x's and add them all together. And then from that number, you're going to subtract the sum of all the x's all together, squared, with that one number squared, divided by the square root of n, and you're going to divide all that by n-1, which is the degrees of freedom. Take a shot. And so that's pretty much all we got for this, right? So you have to calculate that to do it. So that's going to be something you have to solve for in these problems. But I'm going to give you the population mean and n you'll be able to get from the formula. So again, here's what we have to do, right? So we have these 10 people, right? And for these 10 people, I'm going to give you the scores, right? So go ahead and start writing the scores in here. The scores are 35, so 35, 70, 82, 94, 61, 49, 87, 55, sorry, 75, what? 99 and 73. Reading is hard, guys. So you can imagine how hard doing math is in front of people. That's a stupid mistake. Okay, so we're going to put all those numbers in there, right? And so Dr. Hill has animated that, and so I have all of those numbers there, right? The first thing you're going to do, and you might as well just sort of always know you're going to have to do this for pretty much everything going forward, you're going to get these scores, and the first thing you're probably going to do is you're going to have to square the scores. We pretty much are always going to have to square everything for the rest of the semester. So we need to square all of these numbers, right? And so let's go ahead and start doing it. So 35 squared is 1225. 70 squared is 4900. 82 squared is 6,724, and so forth and so on. Look at there. Yeah, I know you guys probably were just really impressed by that, weren't you? Probably like, oh, Dr. Hill could do that in his head. Nope, Dr. Hill has notes right here, and I wrote down what the first three were going to be. And so, yeah, don't think that I'm that smart, because I'm not. Clearly, I would have to do all that math myself. Okay, now we have all this laid out, right? And when we have this all laid out, what we do is basically we have to always got to get the sums of things, right? We're always going to need the sum of x, right? We need that for this part of the formula for the sample standard deviation, and we need the sum of all the x squares, right? Because that's what this thing says too. It says, right? It says sum all the x. It says square all the x's and then add them all together. So we have to do that. So let's go ahead and do that math. Actually, I have it all programmed, but I want you guys to go through the process of doing it, right? So we need to add all those things together. So it's going to be 35 plus 70 plus 82 plus 94 plus 61 plus 49 plus 87 plus 75 plus 99 plus 73 should equal 725, and I know for a fact that is the answer because I'm going to show it to you in a second. And then we can do the same thing on the other side, so you guys go ahead and start adding all those up. We need to get n, which is going to be 10, right? And if n is 10, that means the degrees of freedom are n minus 1. Take a shot. Basically, what that means is that the degrees of freedom are going to be 9. So we got that 725. So let's go ahead and make that stuff all pop up. That's 725 plus 10 plus 9. And then we have to add all those things up. And hopefully you guys have done that as I've been talking here. That is going to be 56,131. So we have all those pieces, right? And we still need to get the mean and the standard deviation. And so here are our formulas for them. But we have all the pieces we need to get them, right? And then the promised land is way down here, okay? So we got to get these two things first so we can get this thing. So the mean is going to be super easy to get, right? It's literally going to equal the sum of all the x's, right? Which is 725. And from that 725, we're going to divide it by n, which is 10. And 725 divided by 10, you don't need a calculator for that, right? It's going to be 72.5. Easy peasy. Now we have to get the sample standard deviation. And again, this says take the sum of all the squared x scores, and from that subtract the quantities, the sum of all the x's and square that number. So square the 725 and divide that by n, which is 10, and then divide all that by n minus 1, which are your degrees of freedom. Okay, so we were already calculated that 72.5, so I went ahead and animated it there. And now we have to do the second part. So now we have to get the square root of all of this, right? So it's going to be the square root of this number, right? So that's going to be that thing, 56,131 minus 725 squared divided by 10, and we're going to put all of that over 9. And if we do all of that, let's do the math together. Let's see if we can get there. It's going to be complicated. Let's see. Okay, so let's do the math. Let's see. It's going to be 725 times 725, which is that number. We're going to divide that by 10, and I have to write this down because I have to put it back in, but that's going to be 52,562.5. Okay, so from that, we've already divided by 10, so let's say 56,131 minus 52,562.5 equals all of that And we're going to divide that number by 9, right? So that gives us 396.5. 396.5 is what we're going to write down there. And I believe we can just hit the square root of that. Okay, yeah, we can just hit the square root. And that gives us 19.91, which is in fact our answer. Okay, so let's pull that up. And look, 19.91. It's like I already knew that was the answer. It's crazy. Okay, and so we're going to put that down here. That is now our estimate of the sample standard deviation. Look at there. We're cooking with gas now, okay? So now we have all the pieces we need to solve this formula, right? We know the population mean is 50, right? So we know what that is. We know that the sample mean is 72.5. And it's very important that you guys sort of understand from an inferential perspective. That's what we're comparing. We're trying to find out whether 72.5 is meaningfully better than 50, okay? And you might go, I guess it could be, but again, we have to sort of account for the fact that we have all this error that we need to, build into the formula here with this stuff down here. Okay, so again, we're comparing whether 72.5 and 50 are different from one another. So that's the top part of our formula for the T formula. So it's going to be 72 minus 50 over 19.91 divided by the square root of 10, okay? And I'm not going to do all the math here for you guys because I already have a program, but you can pause the video and do it yourself to see if you get the right answer, which should be 3.57, okay? Easy peasy. So once we have that, we do step 4, right? Which is draw our conclusion, okay? And what we have to do is we have to look at the picture that we drew in step 2, and I've pasted it here for you to see. And we have to then, say where it lands in respect to that. So you can already see, right? 1.83 was the number we had to beat, and we in fact did beat it, right? We are out here at 3.57, and it falls in the area where we say we're going to reject the null hypothesis. And now we have to write the conclusion, and the conclusion, just like it did with the z-test, has to say these 3 things. It has to say, 1, what you're doing with the null hypothesis, whether you're rejecting it or retaining it. 2, you have to say why in a meaningful way that'll tell people what happened in the study. And then 3, you have to tell us what the alpha level was, okay? So what you should write for something like this would be reject HO, right? Because we're rejecting the null hypothesis because we're out here. And you're going to say students rated themselves as significantly better drivers than average, right? You can actually put that significantly in there because now you can say that with certainty, right? But this is also perfectly fine. They did rate themselves as higher. That 72.5 is significantly better than average, right? And so this proves, at least with respect to driving, that the better than average effect is real. Look at that. Social psychology work. Now, hypothesis test determines whether this observed data that we saw, right, that 72.5 is different from what you'd expect by chance, right? That's what it literally means out there, right? It says that that 72.5 is so different from what you might expect to get if the null hypothesis is true. And that's all it tells you. It's just a statistical test. It doesn't tell you whether it's big, right? It doesn't tell you whether it's a large effect, whether it's a small effect, whether it's a medium effect, okay? And this is an important thing we need to understand about in statistics. And this is sort of where the field is moving in general. So I want you guys to be very cognizant of there's this difference between saying something is statistically significantly different from chance versus saying this is a large effect or a medium effect or a small effect. And when we're talking about the size of the effect, that's what we call the effect size. Look at there, we're creative in psychology or statistics or whoever develops this stuff, right? So we need to come up with some sort of way of doing that. And the thing is that very small effects can be significant with a large N. You guys learned this when you sort of learned these different rules about the standard error and all that stuff, right? You can make things be significant just by getting a ton of people. If you have 10,000 people doing your study, I don't care what you're doing a study on, you have enough statistical power to find almost anything, okay? And so what it'll find is very, very small effects, right? Because remember, you're going to take that standard error, right? The standard deviation of the sample or of the population, if it's a z-test, right? And you're going to divide that by the square root of n. Well, the bigger n is, the smaller that whole bottom part ends up being. And if you're dividing that whole top part by a smaller number on the bottom, as long as n is super large, right, you can basically make that whole thing go down to practically 0. Like, you can make it super duper small, which makes it super easy to find something significant. So you can increase your statistical power just by adding more people to your study. But it doesn't tell you whether or not the effect is actually large. So that same mean difference, that same 10 points, it might be significant for one study with 100 people, but not significant if you only had 10 people. Right? Because again, the number of people increases the statistical power. So we always have to say, and you have to think about this going forward, and you might as well sort of start keeping track of these things because this is a big part of the final exam where I'm going to sort of ask you, I'm going to give you a setup, and you're going to have to determine, whether I'm asking you to give me a test of statistical significance, which is a t-test, versus a measure of effect size, which we're going to learn two of them today, Cohen's d or r squared, okay? So whenever we do a hypothesis test, from this point forward, we're also going to come up with some type of measure of effect size, okay? To tell people, yes, this effect is significantly different from 0. That's what our statistical significance test tells us, what we've learned in a t-test and a z-test so far. But then we're also going to say, yes, they're significantly different and it is a large effect. And it's a whole separate set of things that tell us the effect size, okay? And you're going to have to be able to distinguish between those things. Now, a fun fact about Z, right? A Z itself, right? The p-value, it was sort of both of them because it told you whether or not the thing was statistically significant, but it also told you how far, how many standard deviations the score was away from the mean. So in and of itself, Z is actually both a test of statistical significance and a test of effect size or a measure of effect size, because of what it does, but it's sort of unique in that regard. All the rest of the things we're going to learn don't work that way. Okay. So, the first measure of effect size we're going to learn is Cohen's d, okay? And so it looks a lot like the formula for the t-statistic, right? Except you don't have this stuff in the square root of the denominator and you're not dividing by the square root of n. So, the estimated Cohen's d is computed using the sample standard deviation, okay? And so again, Cohen's d is going to be the mean difference, so that same top part of the formula, right, divided by the sample standard deviation. So it's not going to be by the standard error, right? Because if this was the sample standard deviation divided by the square root of n, then you would be solving for t again, right? So we're not going to use the standard error. We're just going to use the sample standard deviation, okay? So for this formula that we just learned for the problem we just did, right, that mean difference, you need to basically put Cohen's d in your head. Is sort of the most popular one that we're going to learn. Cohen's d is basically equal to that 72.5 minus 50, right? Because that was the top part of the formula that still stays in the formula for Cohen's d. And we're going to divide that by 19.91, right? That was the sample standard deviation, okay? And we get 1.13. And this you interpret just like z-score, right? You're saying that these two scores, right? This is literally the formula for like the z-score, right? The basic z-score formula without accounting for the n. And so what this literally reads as is that 72.5 is 1.13 standard deviations above. And you can kind of see that if you sort of figure it out, right? Because what's the difference between these two things, right? It's like 22.5 points. Well, 19.91 points is one standard deviation. So that rest of that difference between 19.91 and 22.5 is 0.13, right? That's the standard. That's how many standard deviations difference it is. Okay. And so this tells you that 1.13 is the amount of standard deviations that these scores differ by. So it puts it in terms of standard deviation units, and you know why we care about doing that, right? We care about doing that primarily, though, because we sort of know, or at least have some ideas based on work that people have done, what constitutes a small, medium, and a large effect, okay? And so what we know is that the rules of thumb for Cohen's d, and you should put these in your brain. So put this formula in your brain, and then put these rules of thumb in your brain. You just need to know these things, right? Because I'm not going to give them to you on the test. So a Cohen's d of 0 means you have no effect whatsoever, right? It would basically mean that there's no mean difference, right? That's the only way you can get that, is that these things are exactly the same. And so if they're not the same, then clearly it's 0 standard deviations away. 0.2 is a small effect. 0.5 is a medium effect, and 0.8, so anything above 0.8 is a large effect. And if you get something that's in between these things, if you get like 0.7, just say it's like a medium to large effect. Don't make it harder than it has to be. These are sort of bookends, I suppose. Just sort of use your brain and figure out what it's supposed to be. But in this particular case, it's obvious, right, that 1.13 is way larger than even 0.8. So this effect, the better than average effect, is not only real, right? It is a strong effect. Those scores aren't just a little bit better than average. People were saying they were way better than average. And frankly, if I were able to sort of get all this information from you guys about your attractiveness, guess what I would find? It would be even stronger. It'd be like 2.7. This first number here would not be 72.5 if we said on a scale of 1 to 100 how attractive you are. It would basically be like 93. Like everybody thinks they're 9s, okay? Because you guys are delusional. That's y'all, not me. I was accurate, right? I went with a strong 7.58, as you can see there. All right, so what do we have next here? We're going to do another example, okay? So this shows you how we sort of use this stuff in real life to sort of answer real world questions. So we're a surgeon. Maybe it's my wife who happens to be a surgeon. Let's see. I wish she would do something like this so we could get rich and retire. But let's say a surgeon develops a new, less invasive technique for repairing a herniated disc in the lumbar region of the back. Okay, so assume that when we get people to surgery, it typically takes them about 64 days to recover, okay, after the surgery. So you get this back surgery and you're down for 64 days until you can sort of get up and start doing stuff again. And so we do this new technique on 25 people. So if you count that up, that should be 25. So based on the data from these 25 people, does the new technique significantly reduce the recovery time? Okay. And so again, for this particular example, we're going to do a one-tail test, and it makes sense to do a one-tail test here too, right? We don't think that this new surgery should make it harder for people to recover, right? Otherwise, it's a new and it's less invasive. So we're using like the little machines that are cutting your back all the way open. We got a little machine and we just do a little cut. So we expect that people are going to be able to recover better because it's not as intensive or as invasive. And so what we're going to do is we're going to do a one-tail test with an alpha of 0.01. Oh, we're going to mix it up here, okay? Now, I want you guys to sort of just look at the data, okay? And because whenever you're doing a statistical analysis, you don't want to just start doing stuff, right? Get a feel for the data and sort of see what you think should happen. Because at some point, you're going to be able to eyeball this stuff and kind of guess what's going to happen. And so if we look at these things, we know the average is 64 days, right? And so if we start at the top, we might go, ooh, look at that. That person took 72 days. He took better. He took more than average, right? That's not good. But this person is a 53, a 52. We got one is 64. We got 1 is 69, and maybe we could play this game where we just say how many people are above 64. So I see 64 days. I see 1. We'll even count him as 2, 3, 4, 5, 6. Yeah, so let's say 6 people. Maybe I missed 1 or 2, right? But 6 of the 25 people are above the 64-day mark in terms, so it took them a lot longer to recover than average, right? But remember, this is the average, so some people are always going to be higher. And everybody else, it seems like they're way lower, right? I mean, we got some 39s in here. That's probably the lowest score. But you can generally see that if you had to sort of guess what this average is, it's probably going to look like it's going to be less than 64, right? So I want you to just be able to look at the data and sort of get a feel for it. And of course, you're going to say, well, Dr. Hale, you wouldn't make an example that wouldn't be significant. So clearly, whatever it is that we're going to come up with for that mean, it's going to be significantly less than 64. Or will it? You don't know. Sometimes Dr. Hale's a crazy person. I do weird things, and maybe I would put an example in there like that just to see if you're paying attention. So let's do our 4-step process. Step 1, we're going to state our 2 hypotheses, okay? So first, we have to state the null hypothesis, which is going to be that the population mean of the people who received the new treatment is going to equal 64 days, right? Because if nothing happens, the mean of the people who got the new treatment should be the same as the people who got the old treatment. So it's going to be 64. The alternative hypothesis, what should it be? You guys go ahead and take a stab at it. Pause it and see. It should be that the H1 colon equals the mu population mean of the new treatment group is less than 64, right? Because we expected them to get better quicker, right? And so it's going to look like this. That's step 1. Step 2, we have to draw our sampling distribution, and we have to sort of figure out what that's supposed to be. So we're going to draw our sampling distribution, and then again, we're doing a one-tail test with alpha, I believe we said 0.10. And so I want you guys to go ahead and look that up on your table. But before you look that up on your table, we're going to go ahead and set up our areas. And remember, we're saying it's going to reduce it, right? So the average is going to be here. So that area where we're expecting to beat is going to be over here. And does that mean we're going to have this thing be a positive t or a negative t? It's going to be a negative, okay? So whatever number you look up, it's got to be negative because it's on this side of the mean. And so that rule that we learned from the Z stuff still applies here. Anything to the left is going to have a negative critical value, right? And it makes sense too, right? Because if you think about it, it's going to be the mean of the group minus the mean of the population. And we're expecting it to be smaller than 64. So something smaller than 64 minus 64 is going to be a negative number, right? So it's going to be over here is what we end up looking for. So if you guys look that up, and you won't be able to find it on this table, right? Because this doesn't go down, but your degrees of freedom should be n-1. So you should be looking in the one-tail 0.01, right? And then go down here and find 24. So whatever that ends up being, it should be negative 2.49 is what you should have come up with in your table. Now you're done with step 2. Yay, that's exciting. I'm very excited. We're almost done, so that makes it even better. Step 3, we have to calculate our test statistic, okay? So again, we need to get the t, and we already know what the degrees of freedom are, and that's what it is. And again, you're going to solve for m and s, and I already gave you the population mean of 64 and n, which is 25, so you got to get those two pieces. That brings us to step 3, calculating the test statistics. So we're going to do a bunch of math just so we can get this t at the bottom, right? And so I'm going to give you the population mean, and I'm going to give you n. And I'm probably going to be nice if I give you this much data to do. I'll probably lay it all out for you, or at least the scores are there. But if I don't give you something more than like 10 people, 10 I'd put in the text and make you have to like do this yourself. But either way, you got the scores, right? And you already know the first thing you're going to do is square the scores. That's what we're going to do basically for the rest of the semester. You got some scores, let's square them, right? So we squared 72, we squared 53, and we went all the way to the end. Once we square all those things, we typically have to add them, right? And we're doing all of that so that we can get the pieces to build this thing, right? Which is the sample standard deviation. So the first thing we have to do is we have to get the sum of all the x's, so we can just add all those together. And if we did that, we should get 1406, okay? And then we need to get the sum of all the x's squared. So that was why we squared them all, right? Because we got to square them so we can add them all together. And if we do that, we get 81,210. And if you don't believe me, you can pause and add it up. In fact, someone should do that and verify if it's right. If it's wrong, remember, I always give extra credit if people find mistakes so that I can fix them later on. We know that n is going to be 25, which means the degrees of freedom, take a shot, or n is n minus 1, so that's going to be 24. And we have to calculate the mean and then the sample standard deviation now, right? And this is the thing that's different. We didn't have to do the sample standard deviation before. So again, let's get the mean, right? The mean is going to be what? It's going to be the sum of all the x's, which is 1406, and we're going to divide that by n, which is 25. So let's bring our calculator up and say 1406 divided by 25 is 56.24, okay? And so if we do all that math, that's what we in fact get, 56.24. So we'll just put that down here as well so that we can see that that's what we're doing. And then we have to get the sample standard deviation, which is the square root of all of this stuff. And what does that stuff all say, right? So this says get the sum of all the x squares. So square them all and then add them together. And that's that number right there. We've done that already. And from that, you're going to subtract the sum of all the x's, that total here, squared, divided by n, and you're going to divide that by the degrees of freedom, which are n minus 1. So let's go ahead and do that, okay? And so if we do that, it's going to equal 81,210, okay? So that minus 1406 squared, right, because that's 1406, and we're going to square it and divide that by 25, and then that whole thing, whatever that all is, we're going to divide that by n minus 1. Which is going to be 24. So let's actually do that too, because that's a lot of math and you actually will have to do it. So can we bring a calculator up? And so if you're going to do that, you have to do the order of operations. So you got to do stuff that's in parentheses first, and then within the parentheses, you then have to exponentiate, right? So let's do 1406 times 1406, because that's what 1406 squared means. And we have all of that, and we're going to divide that by 25, and that gives us 79,073.44, okay? And so write that down somewhere. Dr. Hill will write it down, 79,073.44. And then we have to go back out here to get this part, right? So it's going to be 81,210 minus 79,073.44. Okay, so we got all of that. Oh, yeah, no, we're fine. Okay, and that's what that ends up getting us, okay? Easy peasy. So that's the difference between those two. And we have to take all of that number right there, right? And we have to divide that by 24. So let's take that and divide it by 24. And it gives us that thing, and we have to get the square root of this number. So we just get the square root, and it's 9.4352. So let's say it's 9.44. We're going to do some rounding here. And that is, in fact, what it is. It's 9.44, which we will then put over here. So now we have all the pieces of information that we need to solve this thing, right? We know that the average was 64 days. And remember, what we're testing is whether 56.24, whether that mean of 56.24 is significantly less number of days of recovery than 64 days, right? And you might say, ooh, that's kind of close. That's not as low as we thought it might be. And so let's actually find out if it is, okay? So the way we would solve that, right? It's going to equal, T is going to equal the mean difference between the two, between our sample mean and the population mean. So 56.24 minus 64. Okay, and we're going to divide that by the estimate of the standard deviation, which we said is 9.44, and we're going to divide that by the square root of n, which is the square root of 25. So we're going to work all that out. And what we do when we get that, we get negative 4.12. And again, it's negative, right? That's why we put that stuff on the left-hand side of the distribution with our one-tailed test, because again, this was going to be smaller. Just like the better than average effect we put on the other side, it's going to be bigger. We don't expect our recovery time to make the treatment worse, so we put it all on the other side for that, and we end up with a negative t-score here. And that's how you do it, because the mean difference switches, okay? So once we got that, we got our magic number. We had to beat 2.49. Did we beat 2.49? Yeah, we did. We're way out here, right? So we're a negative 0.412. So what can we conclude on the basis of this, right? You didn't look at that picture, and when you saw that it was 56, right? You said, well, 56.24, that doesn't seem like it's that much less than 64, but it in fact was, okay? And so what we're going to do is we're going to say we're going to reject the null hypothesis, right? Because we're out of here. And what you would write is something like, the new procedure significantly reduced the number of days needed for recovery, right? You went from having 64 days on average to having 56 days on average, okay? And you're going to say P less than 0.01, right? This is less than 0.01. Be careful with that, because that's what our alpha was. It wasn't 0.05, okay?